Previously, we defined a probability space. We defined conditional probability, and we talked about independence. Today, we'll talk about random variables. A random variable, given a probability space omega, f, and p, a random variable x is a measurable function. Particularly, it's a mapping from the sample space omega to real numbers. But it's such a mapping that it is measurable, by which we mean that all Borel sets defined on the real numbers have inverse images in the sigma algebra F. That is, when we have a mapping, in order for it to be a well-defined random variable for our probability space, we have to be able to measure the probabilities of all the inverse images going from the value of the random variable back to the sample space. Okay, so to illustrate that, let's begin with the simplest example of tossing a coin twice. Remember, we had 4 possible outcomes: HH, TH, HT, TT. Okay, let's define a random variable x1 of w as the number of heads occurring in the outcome w. Okay, so w's are all elements in the sample space, and each of these elements map to a value under this mapping x of w. Okay, so in particular, in this example, HH will map to the value 2 because it has 2 heads, right? TH and HT both map to 1, and TT maps to 0. Okay, now let's check that this is a valid random variable. We need to check the inverse images, right? So let's see. W such that x of w is in some interval a to b. Okay, this is the inverse mapping. Is this a part of f? Well, it depends on what f is, right? Suppose f is the set of all subsets of omega. In this case, the answer is going to be yes. You can see that by checking, for example, what are all w's such that x of w is in, for example, 0 to 1.5. Well, 0 to 1.5, 0 not included, that into this interval, only this outcome TH, HT maps, right? So, however, on the other hand, if W maps to 0 to 1.5 inclusive, where 0 is included, in that case, we would have HH as well, right? no, TT as well. So TT, TH, HT. Okay, so if this is F, then this random variable is a valid random variable. However, if we chose, for example, if F was, for example, the following: empty set omega, let's see, TH, HT, HHTT, if you remember from the first lecture, then under this, for this sigma algebra, or for this algebra, okay, x1 of w would not be well defined, will not be a well-defined random variable, okay, because this, right, the inverse image of this interval 0 to 1.5 is not included. So the event TT, TH, HT is not in, let's call this F2, is not in F2. Okay, so you know, I gave this example just to illustrate that a random variable is defined with respect to a probability space which comes with not only the sample space, but the sigma algebra associated with that sigma sample space. All right, so let's now discuss some facts that follow through this definition of a random variable. When you sum random variables, okay, you get a random variable. I mean, because when you sum two functions like this, x of w and y of w, the sum is f measurable. Okay, it's easy to show this. You could show this as exercise. Similarly, a product of random variables is a random variable. Okay. Similarly, a function of a random variable is a random variable as well, which you could also prove as exercise. Let's see an example of a function of a random variable. Suppose y is defined as x squared, and x is this, let's see, x1 squared, where x1 is this random variable that we define here. All right, so in this case, what is the range of y? The range of y is, well, when x1 is 0, y is 0, x1 is 1, y is 1. When x1 is 2, y is 4. Okay, so this is, these are all the values that y gets. Now, what is the inverse mapping of, what is w such that y is in the interval, let's say, 1 to 5. Well, that the inverse image of 1 to 5 is so basically, when y takes the value 4, x takes the value 2, so that is w such that x of w is 2, and that is the event HH. Okay. Now, an important example of a very simple binary random variable is the indicator function. The indicator function of an event A, okay, in F indicates whether or not that event happened. Okay, so IA of W is equal to 1 if W is in A, if the outcome is in A, which means A happened, and 0 if W is not in A. All right, so so clearly this is a valid random variable because W such that IA of W is 1 is the event A, which is by definition in F. W such that IA is 0 is A complement, which is by definition, since F is a field, A complement is in F, right? So that's also included in F. So indicator functions are very, very useful. We will make use of indicator functions throughout the rest of the course. Here is an example where that combines the definition of indicator function with the fact that sum of random variables is a random variable. Often we sum indicator functions in probability models that deal with repeated experiments. So suppose we are thinking of a repeated experiment as follows. We take a radar reading at each minute. Every minute we take a reading. The reading is either indicates that there is a target or not. Okay, and every minute there's a new reading. Okay, so one may ask for the total number of readings in 1 hour, and then in order to compute that, we could sum up the reading indicator functions over 60 seconds. So let's formulate this as example 4. Okay, so AT is the event that there is a positive reading at time t. Okay, and let S be the total readings, total number of readings in 0 to 59. Okay, so over an hour. Okay, now we could always write S as the sum t from 0 to 59 of IA sub t, where IA sub t is either 1 if there is a reading at time t, and 0 otherwise. Okay, so a sum of indicator functions is a random variable that we will make use of a lot, especially when we do independent trials, independent Bernoulli trials. For example, tossing a coin repeatedly and counting the number of heads. We will make use of the sum of indicator functions, and we will discuss this further in the coming lectures.